the recording. Yeah, is my screen visible? Is the screen visible?
Yes.
Okay, so let me start. So what I'm going to do is I'm going to go over the concepts once, and then we'll take up problems accordingly. So the first part is statistics. So basically, statistics is the art of learning from data, and there are two types of statistics: descriptive statistics and inferential statistics. So here in stat 1 we mainly focus on descriptive statistics. So firstly, we talk about population and sample. So population is the total collection of all elements. So for example, um, one second. So this is the say the population has got yellow balls and green balls. So when we take a sample out of it, a sample will be a subset of the population. So when we take a sample out of it, the sample will also contain blue balls and green balls. So basically sample should represent the population correctly, so as to that we make correct inferences out of it. So the observations are correct. So if the sample does not correctly represent the population, then our entire statistical analysis will it get affected. So there are two um, one second. Okay. Okay. So descriptive statistics and inferential statistics. Descriptive statistics is used for describing and summarizing the data. Uh, when we describe or summarize the data, it can be done either on the population or on the sample. But when we are drawing conclusions in inferential statistics, then it is only done on the sample. So the next part we'll talk about variables and cases. So basically, a data can be, before going into variables and cases, it's related to this. So a data can be unstructured or structured. So when a data is unstructured, you can think of it as a picture, comments in the comment section, or social media post, or anything like that. So that is unstructured data. Structured data is usually in tabular form. So when we write the data in, I'm sorry, the lines are dancing. So when the data is in tabular form, we have certain variables. Okay, for example, there is a table of student data. Okay, so there will be name of student, say A1, A2. These are the names of students, and for each student, say we record roll number, marks. So these are the variables. Each of the row, these are the variables, and uh, no, I'm so sorry. So each of the rows represent the cases, and the columns represent the variables, the attributes, the basic properties of the each of the cases or observations. Cases are also known as observations. So these are the rows, and for each row we record roll number, marks, gender, etc. So these columns are the variables, and each of the column has its own unit. So a variable has same unit, marks has same unit. Okay. um, so if you have any questions you can ask, if anything that I'm explaining, if that is not clear, then you can ask also. The next part is, so data can be uh, data can be categorical, data can be numerical. Categorical data are of two types and numerical data of two types. Categorical data are nominal, ordinal, and numerical data are of two types, interval and ratio. So nominal data only has labels. For example, say gender. This is a label. Um, Ordinal data has labels. Yes, the session is getting recorded. Okay. So nominal data has labels, ordinal data has labels and order. For example, rating, some say rating into good, bad, um, average. Okay. So how the order will be from low to high, bad, average, good. Um, I'm not sure about CT. I think you can ask the secretary about this. Okay. So I'll continue. right? So okay, so for interval, um, the variable, uh, this kind of data will have label. This kind of data have label. It will have order, and you can take differences, right? For example, temperature. Example is temperature. But you can say temperature is high, temperature is low. You can take differences between two temperatures, but you can't say absolute zero for temperature is just a number. You can't take absolute zero for it has no meaning actually. So when you say 20 degrees Celsius, 40 degrees Celsius, it's not really double the temperature, although the number feels like that. So in the ratio you have, you can take, it has absolute zero. You can take ratio. You can take ratio. So usually, uh, like measurement of something, measurement of say length, right? So the next part we are going to look at time series data, and okay, I'll have to be faster. I'll have to go over faster in order to cover most of the things. Kelvin scale of temperature. Yes, in that sense, see, it has absolute zero in Kelvin scale of temperature, but you still can't say that it is ratio, because if you take proportion of two temperature, it actually means nothing. Kelvin scale has one temperature as zero, Celsius has another as zero, Fahrenheit has another as zero. So that means nothing. Okay, which is why you can't place it in ratio category of data, right? So the next portion we talk about time series and cross sectional data. So in time series data, when you are looking at a data over a period of time, say for example, you're looking at say temperature of Chennai, um, say over a period of 7 days. Okay, so you are basically observing the temperature for a period of 7 days. So that's why this is time series data. uh, Say when you are observing the temperature of four different cities, say Chennai, Delhi, Kolkata, and Mumbai. Okay, when you're observing four different variables, say during uh, at a particular time. Okay, so say at 12 p.m. for example, this is just an example. Okay, so that will be an example of cross-sectional data. So these are the main types of data. The next we will look at frequency distribution, how we make a frequency distribution table and what is relative frequency. This is the next portion. So you have say category, we look at a table category, A, B, C and D, and then say A occurs 4 times, B occurs 2 times, C occurs 2 times, and D 2 times. So total is 10. Then the relative frequency will be um, 4 by 10. The frequency divided by the total. Okay. So 4 by 10. That's how we calculate the relative frequency. Okay. Then this will be 0.2. Right. So this is how we create frequency distribution table, and this we did for categorical data. Okay. So when we have categorical data, we um, discretely put all the categories in a column, list out the frequency, and to calculate relative frequency, we divide the frequency by total. What if we have uh, numerical data? Okay, what if we have numerical data? Then what we will do? This okay. First, we will look at how we describe categorical data. Then we go to the description of numerical data. So to describe this kind of frequency table, we mainly use pie chart and bar chart. There is pie chart, there is bar chart, and there is Pareto chart. Okay, so pie chart is pie chart basically is a circular chart which uh, in which the categories look like the pieces of pie, and this angle is calculated by multiplying the relative frequency with 360 degree. So that gives the angle for a given category. So the relative frequency we choose and we multiply it by 360 to get the angle of the pie chart. For bar chart can look like this. So it looks like lines. Vertical lines, or it can be horizontal lines. The x-axis has the category, and the y-axis in the bar chart can represent frequency or relative frequency. In Pareto chart, when the frequency is sorted for bar chart, then it is Pareto chart. So for Pareto chart, the bars will be either in ascending order or in descending order. Okay. So this is how we describe the categorical data. Um, Next we go to description of numerical data. So description of numerical data is it's like, so when you have numerical data, you have a complete range, say um, 10 to 20, 20 to 30, 30 to 40, 40 to 50. So this is how we, because in numerical data it is uh, interval ratio, so the number that can happen, that's continuous. Okay, so which is why it has to be divided into ranges, and for each range we um, list out the frequencies, and accordingly uh, we get the total here, and for each total we find out the relative frequency. Okay, right. So this is basically the table for categorical data and a table for numerical data. So next we look at mean, median, mode. Okay, mode is basically the most common category. So here for example, uh, the mode of this given data is category A, because the category A happens most frequently, so mode is the most frequently occurring category. Mean is the average. uh, Mean is, we find mean for the numerical data um, when we say that bimodal and multimodal data. Okay, let me copy this. So bimodal and multimodal data. So if two or more categories have the highest frequency, for example, if this was one, um, if this was one, then the total here would be seven. Okay. Anyway, never mind. So here the total would be 7, and this relative frequency will be 0.1. So what I'm trying to say is, here category B has frequency 2, C has 2, D has 2. So all three of them have has frequency 2, and frequency 2 is the highest frequency, which means that this is multimodal data, because this particular data has more than two highest frequency. Okay, so next is median. Median is defined only for ordinal data. So
Ma'am,
yeah,
how is it multimodal? It has only one model, na? One model.
multimodal by definition is the highest frequency occurs in more than two categories. So in this particular example, the highest frequency, which is 2, is occurring in three category, right? So which is why this is your multimodal data. Okay. The next is median. So 1 second.
Ma'am,
Yeah.
Like one is occurring two times and two is also occurring two times, then its mode will be frequency one.
One is not occurring two times. No, the category
No,
A, which has frequency one. Say like
no,
this.
I'm just saying if one will occur two times, like in A and also in B,
Hmm.
and two is occurring in C and D,
Hmm.
then its mode will be one and two both, right?
Say it again. One is
Like,
occurring two times, right? You're saying
yes.
A occurs two times.
No, A occur one, A's frequency is one,
A's frequency is one, yes. A's frequency is one.
and B's frequency is also one.
Okay,
C's frequency is two,
okay.
and D's frequency is also two.
Yeah, then it will be bimodal data because
Mm,
the mode frequency occurs in two variables, which is why that will be
yeah.
bimodal data. Okay,
Okay.
and the in the given table it occurs in three, which is why it is multimodal data. Right, I think okay, do you want to continue with revision, or should I just go over only the important topics?
My doubt is most of my doubts are in probability. Before
Okay,
that, it's easy, I think.
okay, fine. So let me skip some part over here and go over to the topic which might have more doubts. Fine.
Yes, yes.
Yes, ma'am.
Okay, so uh, I go to the topic of descriptive measure. For descriptive measure, there is mean, median, measures of central tendency. So when a data set is given, and we can, in a data set, to describe it we can use two measures. First is measure of central tendency, another is measure of dispersion. Right. So for mean, there are two kinds of mean. One is the sample mean, another is the population mean. So it's just that for mean you take the sum of all the observations and divide it by n, and when you divide it by n it is sample mean, and when you divide it by uh, capital N, which is basically the number of values in the population, so that is the capital N, so that is your population mean. And for sample mean you are dividing it by the total number of in the sample. um, for group data, okay, I think these are the easier topics. Most of you might have doubt in probability, and I guess we are running out of time, so um, standard deviation, okay. Okay, so we have done mean, and we'll do variance because variance is also important for probability. So for variance, variance is basically the deviation from the measure of central value. uh, so what do we do? Say the mean is x bar, then variance will be uh, x1 minus x bar whole square plus x2 minus x bar whole square, xn minus x bar whole square divided by n. So that will be your variance. And when we take the square root of variance, that will be your standard deviation. Um, in this, another important topic is there, which is your covariance and correlation.
Ma'am,
So, yeah,
can you please explain what will happen if we multiply a constant in variance and in standard deviation?
yeah, sure. So basically, when you add a value to the mean, then the mean comes out same. When you uh, say you add, oh, did I say same? Same is for the variance, okay? So when you add a value to the mean, says you have added c to all the values, x1 plus c, x2 plus c, xn plus c, then the mean will come out as xn bar plus c. uh, when you multiply c to each of the values, are you understanding? Say you have a constant, c is a constant, okay, and the new observations are x1 plus c, x2 plus c, xn plus c, okay. So the new mean is going to be x bar plus c. If you multiply it, cx1, cx2, cxn, then the new mean will be cx bar. In case of variance, it will, one second. Yes. So in case of variance, it will remain same, which I said before. In case of variance, the new variance will be equal to the old variance. And when you are multiplying it to some constant, then the new variance it will be equal to c square into old variance. In case of standard deviation, it will be square root. So for standard deviation, the new standard deviation, that will be equal to the old standard deviation. And in case of new uh, for for this one, this will be equal to the old standard deviation. For this one, the new standard deviation will be c times the old standard deviation. Yeah, is that fine? Is
Ah,
that
yes,
clear?
ma'am. Thank you.
Yes, ma'am.
Clear,
Okay.
ma'am.
Okay, so um, next time going to next time going to covariance and correlation. One second. Okay. So variance. Say we need to find association between two data. Yes, I am going towards the topics of probability, which is why I am rushing these topics. Okay, so covariance and correlation is like the formula is important. I think you will have question from here because the mock test has, I think, some question from this topic. So after this, I'll go towards the topics of probability. Fine, I'll do the questions also. Okay. So covariance. So basically, we are trying to find the association between two variables. So in order to find the association between, this is for association between two numerical variables. So covariance gives the strength of linear association between two numerical variables, and you can see that, say, x is a numerical variable, y is another numerical variable, then covariance of x and y will give xi minus x bar, yi minus y bar, divided by n, and I runs from 1 to n. What this means is that x contains x1, x2, x3, xn, and y contains y1, y2, y3, yn. So x bar is mean of x, and y bar is mean of y. So we are trying to find the strength of linear association using this, and see this formula of variance is so like it looks almost similar to the formula of variance. In variance we had xi minus x bar whole square. So here, instead of xi minus x bar whole square, we have xy minus x bar into yi minus y bar and divided by n. So this is a way to, the pattern is a way to remember the formula of covariance. Um, Next is your correlation. Correlation is the measure of linear association between the two numerical variables. Um, so same here, you have these two x and y. X has x1, x2, xn. Y has y1, y2, yn. So the way to calculate correlation coefficient will be, R is your correlation coefficient. So to find that, you have to divide covariance of x and y by the standard deviation of x and standard deviation of y. Okay, this. Um, so when you simplify it, you get here xi minus x sigma xi minus x into yi minus y bar, and this is I1 to n, and divided by, for standard deviation you have to xi minus x bar whole square root over sigma is summation. For summation we use the symbol of sigma. Okay, so that is basically the formula for calculating the correlation coefficient. I think we here have a question for correlation coefficient. Um, 1 minute, let me. Yeah, so this is the question. Okay, is the question visible? Is this visible?
Yeah.
Okay. So, what can be said about the correlation coefficient R of x and y, where y is equal to minus x square minus 3x minus y minus 5. X takes the values of first 20 positive integers. Anybody wants to try it? Okay, no problem. In this question, you don't really have to calculate. Just notice that y is, if you take the negative sign common, then y is minus into x square plus 3x plus 5. So for any positive x, if the values of x increase, then values of y will continue to decrease. So, which is why in this question the correct answer is the C option. Okay, so next we go to
Ma'am, can you repeat
permutation.
that?
Yeah, so here notice that y is minus x square plus 3x plus 5. Okay, so if x keeps on increasing, if we increase the value of x, if we continue to increase the value of x, then uh, y will be minus of bigger and bigger number, right? So if y is say first minus 14, then minus 15, then minus 16, because we are increasing x, so the y is decreasing, right? So if y decreases as x increases, then correlation coefficient is between 0 and minus 1. Okay, so next we go into um, permutation combination. For permutation combination, okay, wait. So in permutation combination you have the principle of counting. Say say for each m times something occurs m times, and for each m of the occurrences something occurs n times. Okay, so you have a red shirt, a yellow shirt, an orange shirt, and for red shirt you have say green trousers or orange trousers. For yellow you have green trousers, orange trousers. For orange shirt you have green trousers, orange trousers. So what is happening here, for uh, each of this occurrence, this happens twice, this happens twice, this happens twice. So for each of the three ways, you have the other happening for each of the three shirts you have trousers, option for trousers too. So the multiplication rule says that the total number of ways this can be counted is 3 into 2. Similarly, for the generalized principle of counting will dictate that uh, if something occurs m1 ways, and for each m1 ways another thing occurs, you have m2 choices. For each of the m2 choices you have m3 choices, and for each m1 m2 m3 choices you have m4 choices, and so on and so forth. Then the general rule of multiplication says that total number of ways this can happen is the product of the whole thing. So that is your generalized principle of counting. Uh, Next we go to factorial. So n factorial is n into n minus 1, n minus 2, so and so forth, up to 1. So uh, when you have n objects and you want to find the permutation of n objects, then the number of ways that happens is n factorial ways. If you have n objects and you want to find the possible permutation of r objects, r distinct objects, then the permutation will be n, n minus 1, n minus r plus 1. Okay, so which is n factorial divided by n minus r factorial. uh, Now if say if repetition is allowed, okay, say you have n distinct objects but repetition is allowed. So by similarly, by generalized principle of counting, this will happen n ways into n ways into n ways into n ways, which is n to the power r ways. This is for um, with repetition, n distinct objects in both cases. This is with repetition and this is without repetition. Okay. Next we talk about combinations. So combination is, we want to find, say uh, let me give an example. Say we have HHH, HHT, HTH, Yeah, sure, sure. I'm going there. Yes, I'm going there. Um, you want me to explain the circular permutation first? This is related actually, which is why I took it up. Okay, fine. I'll tell circular permutation before this then.
No, ma'am, go as you want, but I was just saying, explain that also.
Okay, sure. So you have HHH, HHT, HTH, HTT, TH, HTH, TTH, TTT. What did I do? Something is repeated, right?
HTH,
Something got repeated. Oh, HTH,
HTH, third and
HTH got
fourth.
repeated. Right. Okay. So, when we are taking, say, two heads and one tail, in the case of combination, two heads and one tail is one option. But when we are taking permutation, then we have to choose the order. This is one order, this is one order for two heads and one tail. But in the case of combination, this is one observation, one way. This is just one way. So, what is happening here? What we are doing, um, n factorial by n minus r factorial is giving us the permutation, and then this is like the repetition and we are dividing it by, so r factorial. So this is, that's why the formula for combination n factorial divided by n minus r factorial into r factorial. So we eliminate the repeated number of ways by dividing the formula of permutation by r factorial. Okay, so I explained this in this manner because many a time when we are studying, looking at the formula, we get confused. We think, where did the formula come from? So, which is why I explained it in this manner. So, next we have circular permutation. So, circular permutation is basically permutation formula. Permutation formula when you have n distinct objects arranged in a circle. So, say this is a circular uh, arrangement, and there are say n points, right? So one has, this is one, okay. So how many places can one be placed? One can be placed in n minus 1 places. Yeah, somebody had a doubt, I think. So no, one can go in n minus 1 places, n distinct n places. Then so it comes out like this. So one of the points can, say you have four people sitting in a table A B C D. Okay, so let me first give the case of 4 points. Say you have 4 points A B C D. Okay, So how many ways can you arrange it? You have to fix one point at one corner. Yeah. So you have to fix one point in the corner. You are fixing A here. So after fixing A here, B has how many options? B can be placed in three places, right? Then after B has been placed somewhere, two places are left. So C can be placed in two places. After C has been placed, only one place is left and D can be placed in that last place. So that is 3 factorial when you have 4 points. So similarly, when you have a circle with n points, so 1 is fixed here and 2 can be placed in n minus 1. So it can go here, it can go here, 4, 5, 6, all the n minus 1 positions are open for 2, right? Next we have the, so 3. 2 is already placed, 1 is already placed. So we have n minus 2 positions left for 3 to fill. So n minus 2, then for 4, n minus 3, and so and so forth. So the last one obviously has only one left, which is why circular permutation is n minus 1 factorial, not n. Somebody wrote n in the comments. Now, say clockwise and anti-clockwise are same. There are n distinct objects, but it is arranged in such a manner that clockwise arrangement and anti-clockwise arrangement are same. So what happens in that case? We have the total in clockwise in circular permutation we got n minus 1 factorial, but when clockwise and anti-clockwise are same, it is symmetrical, which is why we have to divide this by 2. So when clockwise and anti-clockwise are same, the number of permutations reduces to n minus 1 factorial by 2. Okay, is that clear?
Ma'am,
Yeah.
what does it mean clockwise and anti-clockwise means? Uh,
Okay, clockwise and anti-clockwise means when you are, say, arranging in this way, this is clockwise.
yes, ma'am.
If you are arranging in this way, this is anti-clockwise. What we are saying in this case is that clockwise and anti-clockwise are same. So when clockwise and anti-clockwise are same, then the number of, otherwise it doesn't. If it is same, then it reduces to n minus 1 factorial divided by 2. Okay. Right. So now we finally start with the topic of probability. So say we have a random experiment. Um, say the random experiment is uh, tossing a coin, for example. So this is a random experiment. Example, any random experiment can be anything. So for a random experiment, we have certain outcomes. So the set of all possible outcomes for a random experiment, that will be your sample space. So sample space will be, say, H and T, heads and tails for tossing a coin. Okay, so this is your sample space. So anything that occurs, any event that occurs from the sample space. So the set of all possible uh, the set of all possible events, if sample space has say n elements, okay, then there can be 2 to the power n possible events, because S can have total possible subsets as 2 to the power n. Okay, so now we are going to look at certain concepts related to probability. Um, so first of all, probability distribution can be discrete and it can be continuous. So when do we say that it is discrete? It can be discrete and it can be continuous, right? So when do we say it is discrete and when do we say it is continuous? So discrete means that the possible values of the random variable. So first of all, what do we mean by the random the possible values of random variable? What do we mean by that? Say uh, say let me take this example that I took a while ago here. Okay, so say we want to examine the event of, I'm so sorry, this got disconnected. Okay, so say we want to examine the event of um, head occurring twice. Oh, this, excuse me, this got disconnected actually. Yeah. Yeah, I'm facing a technical issue. Just give me a minute. Is this working now? Okay, I think it's working.
Yes, sir.
Right. So I was explaining the random variable sample space. Uh, so basically, a random experiment is anything which we are observing and it gives an outcome. And sample space is the set of all possible outcomes uh, when that experiment occurs. Okay. So uh, Now, for example, we have tossed a coin 3 times, and for that tossing of coin, we are looking at uh, the probability um, of head occurring twice, right? So we need to count how many times head occurs twice. Uh, this occurs twice once, and this occurs twice 2 times. So our event is head occurs twice. So for that, and we have tossed the coin 3 times. So for that, we have to see uh, what is the value. So head can occur once, head can occur twice, head can occur thrice. But this is not the value we are considering. We are considering head occurs twice. So for discrete probability distribution, we should be able to count. Okay, and for continuous probability distribution, we cannot count like 1, 2, 3, 4. We cannot count like this, right? So for continuous probability distribution, the function is like we are measure like for example when we are measuring something, uh, then the scale is like say 15.2, 15.4, 30.2. So they are infinite, right? So it is like an interval between say minus infinity to infinity. We cannot really count here. So that kind of probability distribution will be continuous probability distribution, right? So now we look at a probability mass function. So for example, uh, the value of random variable is 0, 1 and 2. Okay, and for x equal to x, so for probability of random variable 0, the probability is 1 by 4. For 1, say the probability is 2 by 4. For random variable 2, the probability is 1 by 4. This is for example we are taking. So what happens here? Uh, Notice that all the probability x equal to x is greater than equal to 0, and the sum of px is equal to x is equal to 1. Okay, for all values of x. So this is xi, and I is from 1 to n. So when first of all, when we write the probability value for each of the random variable, that is our probability distribution, right? So this is a probability distribution, and for these individual all probability mass function values, all the sum of that should be equal to 1. Okay, so this is for discrete probability. For continuous probability distribution, we don't have mass function, because notice that we are calculating the mass for individual values. So for continuous distribution, we'll go there shortly. First, let me go over the discrete probability distribution once. Okay, now the next function The next function is cumulative distribution function. Okay, so cumulative distribution function is basically say cumulative distribution function is say f of um so p of x less equal to x. This is capital X and p of x is less equal to small x. So this is basically the sum of probability mass function. So if you say probability distribution function fx is p of all the probability mass function where x is less equal to x. Okay, so up to x, up to the last value of x. Wait, I did not write it correctly. um, this will be like this. So all the, say for example, if I say f of 1 from the previous example, then that will be p of x less equal to 1, which means it will be p of x equal to 0 plus p of x equal to 1, which will be 1 by 4 plus 2 by 4, which is 3 by 4. So this is cumulative distribution function, which will be for a given value. Uh, the next is expectation. So expectation is weighted average of possible value of random variable. So what do we mean by weighted average? So you have expectation, then for x equal to small x1, x2, xn, then weighted average is xi into p of x equal to xi, and we sum this over I equal to 1 to n, and that will be your expectation. And for variance, it is going to be expectation of e minus mu whole square, where mu is the mean. Okay, then this is e of x square minus 2x mu plus mu square, which is e of x square minus e of x whole square. So basically what we are going to do is this will e of x square minus 2 mu e of x plus mu square. So this is mean. So mean is e of x, right? So this becomes minus 2 mu square. So minus 2 mu square and plus mu square becomes minus mu square, and mu is what? Mu is ex. So minus mu square, this e x square minus ex whole square, this is your variance. So we are going to look at some probability distribution, and we are going to look at their functions. Okay, so the first one is your Bernoulli random variable. Uh, so Bernoulli random variable is basically, if say this particular example where we are tossing a coin and we can have at most two outcomes. Those two outcomes is either a head or a tail. So here, say we give the value 0 to head and 1 to tail. Okay. So in Bernoulli random variable, the value of random variable is 0 or 1. Uh, I think. Okay, are you a student, Nishant? I think somebody joined from ID which is not IITM email.
Yes, ma'am, I am a student.
Okay, I think you should have joined from your student email anyway.
Okay, ma'am.
So, where was I? So, Bernoulli random variable x is 0, 1, p of x equal to xi. So, for the value of, basically you can also say another example, say pass or fail a driving test. Okay, pass or fail a driving test. So the pass will be random variable 1 and fail will be random variable 0, and the probability for random variable 1 will be p. Then we have only two random variables, so for 0 the probability will be 1 minus p. So this, what is this then? This is the probability mass function. Okay, so if this is the probability mass function, then what will be the CDF function for Bernoulli? CDF is cumulative distribution function. So we just discussed here that cumulative distribution function is, say if we are finding it at value 1, then that means basically PMF for all x less equal to 1, so which is P of x equal to 0 plus P of x equal to 1. So similarly here CDF, if we the function will be 0 if x is less than 0. Okay, because we have only value 0 and 1, and when x is greater than equal to 0 and less than 1, then the value will be 1 minus p, and if if x is greater than or equal to 1, then it will be p plus 1 minus p, so CDF will be 1. Okay, now what will be the expectation? Expectation will be 0 into 1 minus p plus 1 into p. So expectation will be p, and what will be the variance? Variance will be e of x square minus ex whole square. So what is that? What is e of x square? E of x square is So for that, e of x square will be x square and p x equal to x. Okay. X equal to xi, where I varies from 1 to n. So here what do we have as x? X is 0, x is 1. So x will be again 0 square is 0, 1 square is 1. So 0 into 1 minus p, right? 0 into 1 minus p plus 1 into p. So e of x square is again p. So this is p, e of x is p, so e of x square, e of x whole square is p square. So p minus p square. So variance is p into 1 minus p. So this is for Bernoulli random variable. So next we go to discrete uniform random variable. So what does it mean? Discrete means the value of random variable will be discrete. Okay. The value of the random variable will be discrete. Say the sample spaces. So for example, consider the experiment of throwing a die. Okay. So if we are throwing a die, then yeah, so I gave the example. Say you are tossing a coin, you're getting a head or getting a tail. So if you say tails, I win. So tails will be the random variable 1 and heads will be random variable 0. So if you find the expectation here, that will be p. So whatever probability of winning is there, that will be your expectation. Uh, that is p. Say pass or fail a driving test. So pass for pass the random variable is 1. Okay, wait, let me write it like this. Um, so this is the random variable fail. For fail we are assigning 0 and for pass we are assigning 1. Okay, so okay, right. So is the example clear? So basically whatever the example means, when you see a question where it is like one event is happening and only two possible outcomes are possible in that. Say pass, fail, head, tail, anything. But only two possible outcomes are there for one experiment happening. So that is the Bernoulli. Yeah, sure. I can do that. Okay, cool. Cool. Uh, so let me go through some of the distribution and then we can move on to the question. I'll be really quick with it. Hmm? So, discrete uniform random variable. Say you are throwing a die, and for each die, there are 6 possible faces that can come. So, 1, 2, 3, 4, 5, and 6. 6 possible faces are possible for throwing a die, and each outcome has uniform probability. So, the probability mass function for each x equal to I is 1 by 6 over here. Why? Because this is uniform and This can be counted, so this is discrete. So discrete uniform. So for discrete uniform, this is the um, probability mass function, uh, and the expectation will come out as, okay, first we look at the CDF. So the CDF will, okay, so this I have taken 1 and 6. So for example, if we had like this, a plus 1, a plus 2, up to b, then the total number of outcomes n is here b minus a plus 1. Then the CDF will be lower integer k, where k can be any of these values, minus a plus 1 divided by n. Okay, this is CDF, means this is f. Okay, then try it. Okay, so this is the CDF, and then the expectation will be a plus b by 2 and the variance will be n square minus 1 by 12. You can calculate this. Here n is this. Here n is this. B minus a plus 1, and expectation will come out as this, variance will come out as this. You can find the expectation and variance for this particular example and check if it is matching or not. Uh, well, so the next is uh, binomial random variable. So binomial random variable is basically a Bernoulli experiment repeating n times. So we have a question here for, okay, where is it? Okay, so this is a good problem. I think this was in your mock test also. So say you have a variance of binomial random variable is plotted against varying values of p. With n kept constant, it is observed that the maximum value of variance is 40. Then what is the value of n? So for binomial random variable, we saw that expectation. Okay, we haven't seen binomial. We are doing binomial right now. So binomial, basically for k successes in n draws, with replacement. Okay, so this is the description of binomial. K successes in n draws with replacement. Uh, in case of Bernoulli, there was only one draw, only one experiment, and in that one experiment, there was either one success or failure. So, in case of binomial, there are successive end draws. Okay, one, two, three, four, many end draws are there, and for each of the end draws, we have to see success, failure, success, failure, success, failure. So, all these end draws are independent of each other. Okay, so if all those end draws are independent of each other, how will the PMF look like? So the PMF will look like this: P of x equal to x. This will be um, NCK, because we said K success. So we are choosing K out of N for success, which is why NCK. Then probability P raised to the power K. Right? P is the probability of success, and then we have chosen K successes, which is why we have multiplied the probability of success K times P raised to the power K, multiplied by 1 minus P raised to power N minus K. So this is the PMF of Bernoulli, binomial random variable, and the expectation of binomial random variable is NP. We have seen that for Bernoulli, the expectation is P and variance is P into 1 minus P. And when we look at binomial, then expectation is N times P and variance is again NP 1 minus P. Now let's look at the problem. The problem is that um, maximum value of variance is 40. So when we say maximum value, then we mean that P should be 0.5, because when P is 0.5, the value of variance is maximum. Okay, so we have to calculate the value of n from this. So what do we have here? We have variance as 40, so n by 2 into this is half, right? So n by 2 into 1 by 2 is equal to 40, which means that n by 4 is equal to 40, which means this is 4 into 40, 160. That is the B option. So next we go to hypergeometric distribution. So how many did we do? We did 3, then we did 4, hypergeometric distribution. So this is for K successes in n draws without replacement. So what do we mean by that? We say that we have a set of balls, and there are certain number of black balls and certain number of white balls. So this is the whole set n, uh, n set of say so many black balls and so many white balls. So how many? For example, we take m black balls and total minus, so n minus m white balls. So out of that we are choosing uh, n balls, small n balls we are choosing, and from that small n balls, some will be black and some will be white. Why did I write choose? Because the event of choosing, and from that event of choosing we are going to calculate the probability. So say we have chosen n balls, and out of n balls x are black, then n minus x are white. So in this case the PMF will be of the probability of choosing a certain black ball will be, first of all we are choosing n out of n, okay, small n out of capital N, that is your total. This will be on denominator. Then what did we do? We have chosen x out of m, and from n minus m we have chosen n minus x. So this is your PDF, uh, sorry, not PDF, probability mass function PMF for hypergeometric distribution. And for this particular distribution, the mean will come out as nm by n, where m is this total number of, we have to take one. So basically for hypergeometric distribution there has to be a set, and we have to divide that set into two disjoint sets. And for here particular black ball and white ball, so we have taken m. So this is, m is this value, and n is how many balls we are taking, that value, and divided by n the total number. Okay, so now let's look at a question for hypergeometric. So say a fruit seller has So a fruit seller has 6 dozen bananas, 12 are rotted. So if a customer wants to purchase some bananas and choose 6 bananas without replacement. So here the value of capital N is 12. Okay. We are choosing 6 bananas. So the value of small n is 6, right? And 6 dozen bananas. And right. So what do we have to find here? Uh, okay. So here the value of small m is 12 because 6 dozen banana. 6 dozen banana means total is 6 dozen. So here small m is 12 and small n is 6 and total number of banana is 6 dozen. So 6 into 12, that's 72. And how many rotten bananas? So we have to find the expectation EX, which is uh, 6 into 12 by 72. Yeah, total is 72. Capital N is 72, small m is 12, small n is 6, and expectation is coming out as 6 into 12 by 72, which is 1. Okay. So, okay. Okay, so this is one more important distribution, Poisson distribution. This is also discrete distribution. So in Poisson distribution, we have a parameter which is lambda, and P of x is, this I am writing the probability mass function. P of x equal to x will come out as e raised to the power minus lambda raised to the power x divided by x factorial. This is the probability mass function for Poisson distribution. When do we use Poisson distribution? Use Poisson distribution when the probability of success is small and number of trials is very large. So uh, basically we want to count something within a fixed interval of time or a fixed interval of space. So in this circumstances we use Poisson distribution, and for that the probability mass function will come out as that, and x will be 0, 1, 2, anything, and lambda is greater than 0. Here expectation is also lambda and variance is also lambda. Okay. Now let's look at a problem for Poisson distribution. Um, so this is the question. So the average number of penalties charged by a police in a day. So you see, you are counting something in a day. Within a fixed time, we are calculating the average number of penalties. What will the average number of penalties in a day for not following traffic rules is 5. Assume that the number of penalties charged on different days are independent and follows a Poisson distribution. Find the probability that less than 4 penalties will be charged in a day. So in this, excuse me. Yeah, so in this particular question, they are asking us to find probability that less than 4 penalties will be charged in a day. So less than 4 penalties means we want to find P of x less than 4. Okay, so this will be basically P of x less than 4, which is P of x is equal to 0 plus P of x is equal to 1 plus P of x is equal to 2 plus P of x is equal to 3. And we have to put the formula for um, this particular formula we are going to use p of x equal to x e raised to power minus lambda into lambda raised to power x divided by x factorial. Okay, so we have been given we are going to put the values of lambda and e right. So I think you can solve this. Here lambda is equal to 5. Value of e is always 2.71828. So this will be 5 raised to the power 0. 0 factorial is 1. This again will be 5 raised to the power 1 factorial. Yeah, so you can calculate the answer. So that's what that's the probability they're asking here. Okay. So what I think we can look at more questions. Okay, let's look at this particular question. So let x be a discrete random variable having probability mass function as this. So we have to find the value of k. In this particular problem, we have to find the value of k. So here, since we have seen the property of probability mass function, the sum of all p of x equal to xi, where what is the value of I? There are three values 0, 1 and 2, so I will be 1, 2 and 3. Okay, so this will be equal to 1. What does it mean? It means that p of x equal to 0 plus p of x equal to 1 plus p of x equal to 2, or I can write it like this. That's say x equal to I and I is 0, 1 and 2. So this is equal to 1. So what does it mean? It means that k into 3c0 divided by 3c3 plus k into 3c1 divided by 3c2 plus k into 3c2 divided by 3c1. It is 1. So now we know the combination formula and we can solve it and find the value of k. Okay. So this is one question. Right. Okay. So I think so let's do one more question and then we can wrap up. This is a question on set theory. Since I did not cover set theory in the discussion, I'm doing this question. So A and B are two mutually exclusive events of sample space S, and A complement and B complement are also mutually exclusive. So what do we have here? We have here A intersection B mutually exclusive means phi. So probability of phi is 0. And we have A complement and B complement also mutually exclusive. So if we know, we can apply the De Morgan's law. What is De Morgan's law? De Morgan's law is A union B whole complement is equal to A complement intersection B complement, and A intersection B whole complement is equal to A complement union B complement. So this is these two laws are De Morgan laws, right? So now we have A complement intersection B complement, so we can write it as A union B whole complement, right? So what will be A union B whole complement? What are we given? We are given probability of A. Probability of A is 0.25, right? So when you have A union B whole complement, you can write it as U minus A union B. Okay. U is the universal set. So yeah, so this is the universal set. Sorry about the shape. This is the universal set, and this is A and this is B. We have been given that they are disjoint. Mutually exclusive means disjoint. So A union B complement is U minus P. Sorry, not P. U universal set minus A union B, which is when we take probability of A union B whole complement, we have 1 minus P of A union B, right? Now, why P of U is always 1, right? So now P of A union B is P of A plus P of B minus P of A intersection B. P of A intersection B is 0. So what do we have? We have P of A union B is equal to 1. So if P of A union B is equal to 1, P of A plus P of B is equal to 1 because A and B are disjoint, right? From this particular equation we have uh, wait a minute. So basically we have A complement and B complement are disjoint. So if A complement and B complement are disjoint, this particular set has probability 0. P of A complement intersection B complement is 0. So this particular probability is 0 because by De Morgan's law this and this are equal. So we have P of A union B is equal to 1. From here we have P of A union B is equal to 1. This is 0. So this is P of A, this is also 0, right? And we just saw that this is 1. So we have P of B is equal to 1 minus P of A, and P of A is given as 0.25. So this is 0.75. Okay. So what have they asked? They have asked P of A into P of B. So P of A into P of B is 0.25 into 0.75. So that is your answer. Okay, so I'm wrapping it up. I hope whatever is explained, you understood it. All the best for your intern. Yeah. Any doubt?
Ma'am,
Yeah.
can you please explain conditional probability in short?
Yeah, sure. So conditional probability is conditional probability. For that we have to discuss right. We have the total law of probability, and from there the conditional probability is coming. Just a second. Right. So let me just copy paste from here so that time is a factor. So the total law of probability states that um, so the total law of probability states that P of A is equal to P of A intersection B plus P of A intersection B complement, right? So which means that P of A given that B occurs multiplied by P of B, or B does not occur. So when B does not occur, that's P of A given that B complement occurs multiplied by P of B complement. So this is the statement for total law of probability. And from here we have the statement for Bayes theorem. Uh, the statement of Bayes theorem states that if A and B are two events, then P of A intersection B will be P of A, P of B into P of A given B, or P of A into P of B given A. So this is the Bayes theorem. This is the Bayes theorem, which states that P of B given A is this P of B into P of A given B divided by P of A. And um, so notice that in this example, um when so when we have when conditional probability, when there is conditional probability, then two events are not independent. Okay, so when two events are independent, then P of A intersection B is P of A into P of B, right? But this does not happen. This is Bayes theorem. For Bayes theorem, um, for Bayes theorem, P of A intersection B is not equal to this. P of A intersection B is clearly, we can see that P of A minus something, right? And here also, if we uh, write it as P of A intersection B, then it will come out as P of B into P of A given B, right? So we have seen this here in the total law of probability. We have written P of A intersection B as this, right? And from here we are deriving the Bayes theorem that P of B given A is this. But when the events are independent, then P of A will be equal to P of A given B, and which is why P of A intersection B will come out as P of A into P of B. And notice that in this particular question, we had P of A intersection B as 0, and P of A and P of B, this was non-zero. So this was not independent, this was conditional. These two variables are conditional, we can say, from the value of probability of A intersection B and the value of P of A into P of B. Okay, so this is the difference between uh, conditional, when in we have to use Bayes theorem, and when the two events are independent. Okay,
Okay,
anything
ma'am.
else? Yeah, anything else?
No, ma'am.
Ma'am, is the graded assignment and the mock test are enough for the end term?
I guess so. I mean, one can't really say what they are going to ask, but to prepare well, I would advise to see all the graded assignment and mock test. You can also check out the previous year question. Uh, there is this website initiative by BS degree students, ACE grade. So you can check their previous year question also, you can solve. So you'll get some practice from there. Okay then. All the best for intern. Yeah. Good night.
Thank you, ma'am. Thanks
Thank
so
you.
much.
Yeah.